Hi, it's time for another math easy solution. Turn to discuss further into modeling with differential equations, and now look at a model for the motion of a spring. So basically we consider the motion of an object with mass m at the end of a vertical spring as shown in the figure below, and I will draw that out. So if you had a spring, let's say vertical and like this, and then you have the spring like that. Let's say this is at its natural or equilibrium position, and you have a mass of m that's hanging at the bottom of this vertical spring. So what I'll call this, if you were to have a graph like this, so this is like that. So at this point right here, we'll call this 0 because this is position 0, this is an x-axis, just describing the height of it. And so then basically at this position, or basically at the 0, what we end up having is, I'll just write this down. So at the 0, this is the equilibrium position, so or its natural, or its natural length. I spelled it wrong. Equilibrium position. So this is if you just leave it as is, that's where it is. So that will be our 0 starting point. So if we were to stretch it, so we'll have something like this, and let's say you were to stretch it all, and then as you can see, it becomes, the spring gets stretched. I'll draw this a bit neater actually, and a bit more realistic. So something like that, and that is their mass m. So it's the same one there. So I'll draw this mass just similar size. Okay. So this is at its stretch. We'll call this point x as well. So it's x-axis, this is a random point x as well. And now basically recall from our earlier video titled Integrals and Work, example 2, Hooke's law, and you can see that in the video link below in the description. I discuss Hooke's law, which says that if the spring is stretched or compressed, so even if you were to go the opposite way, so instead of just going down, if you were to go upwards as well, what happens is, if you were to stretch x units from its natural length, it exerts a force that is proportional to x. And this makes sense because, as you can see, when you pull a spring farther and farther, it becomes harder and harder to pull it. So again, that force that needed to pull it is going to be proportional to x. So it would actually increase how much force you need to push down on it as this x, or as the length gets more and more. So in other words, you could write this out as basically the writing Hooke's law. So the restoring force, so that a spring is stretched, again, x units from the natural length, it exerts a force that is proportional to x, and that is the restoring force, trying to restore it back to the equilibrium position. So whenever you pull down, it's trying to go back down to normal. So restoring force, and this equals to negative kx. And the reason it's negative here, so this is just a constant k, it's negative because the force is going up. So if you're pushing down, there is a restoring force like that. That's pushing up. So that is the negative force. It's basically opposite of the one you're pushing. And again, where k is a positive constant, called the spring constant. So now if we ignore any external resisting forces due to resistance, friction, or any losses in energy or whatnot, or heat, heat when you pull the spring, so then by Newton's second law, which states force equals mass times acceleration, we have, again, it's a force. That's the, by Hooke's law, it's a restoring force, and force by Newton's second law is force equals mass times acceleration. So that restoring force, we'll call it F, is equal to mass times acceleration, or we could write, again, acceleration, this is of this object, and since we know its position x, this is equal to, well, the second derivative. Remember, acceleration is the derivative of the velocity, and velocity is the derivative of the position. So this just equals to d squared md2 like that, or the second derivative of x dx squared. And again, this is just a notation for the derivative and the second derivative of x. And again, this equals to now our kx like that. So what we end up having is a differential equation. Yeah, now this is an example of what is called a second order differential equation because it contains a function and its second derivatives, as opposed to my earlier video I went over population growth, which was just a first order differential equation because it had only the first derivative and its function, like that. So let's see what we can guess about the form of the solution directly from the equation. Yeah, so we're going to be doing some guessing work on what the solution is. Later videos I'll go over more explicit ways of finding the solution. But before that, let's rewrite this above equation in the form of, well, the second derivative dx squared, and then divide by the mass and move the mass on the other side. So we have a negative kmx like that, and I'll circle that. Let's do a better box. So one more time. Okay. Yeah, so now that we moved that m away, so we have this equation, and this equation says that the second derivative of x is proportional to itself, or to x, but has the opposite sign of this negative. So we actually already know two functions with this property, the sine and cosine functions. For example, if you were to take the derivative d over dx of sine, let's go, sine of x, this equals 2, basically like I showed in my earlier videos, this just equals to cosine of x. Actually, I'll write this all into one giant thing. So the derivative like this, the second derivative is equal to the first derivative, the first derivative d over dx of d sine x over dx. So this is exactly just what the second derivative means. We're taking the second derivative. So we take the first derivative of the inside function. This is the derivative of sine is cosine, so we have d over dx cosine of x. And the derivative of cosine, what we end up having now, this equals 2, well, that's just negative sine of x. So the second derivative of sine is equal to negative sine of x. So in other words, it's equal to itself, but negative, and exactly similar to this. So the second derivative is equal to negative, it's proportional to the negative of itself. So similarly, if we're looking at cosine is the same thing. Similarly, what we have is the second derivative d over dx squared of cosine of x. This equals 2 d over dx and then d over dx of cosine. So this is exactly what the second derivative means, like that. And again, this equals to the derivative of cosine, that's just negative sine. And the derivative of negative sine, that's just going to be, well, negative cosine. So again, these are pretty pretty telling functions of that are similar to this differential equation we want to solve. Because as you can see, the second derivative of cosine of x is equal to the negative of itself. Yeah, so this will help in our guesswork of what the solution is, trying to guess what the solution to this equation should be in the form of. And in fact, it turns out that all solutions of the above second order differential equation, so this one, so it turns out that all of the solutions above can be written as combinations of certain sine and cosine functions, and I'll go over these in later videos, so stay tuned for that. And this is not surprising because we expect the spring to oscillate about its equilibrium position, so it's natural to think that trigonometric functions are involved. So if you think about the spring, so as you can see, it's going to be going up and down because of the spring. I'll just draw that spring like this. So as you can see, when you pull it down, you're going to have it to go down. When you pull it up, etc. And then as you let it go, it will go back and forth, etc. Like back and forth. If you were to graph the position through time, looks something like this. And again, these are just these are just wave functions. And again, and recall how trigonometric functions look like. They look, sine and cosine also look like this. So this is similar to sine, cosine. And again, make sure to watch my earlier videos on sine and cosine to get a better idea. But yeah, that's pretty much it. So yeah, oscillations. Basically anything that oscillates, it's almost always modeled by trigonometric functions. Anyway, that's all for today. If you learned from this pretty interesting video and this interesting introduction to motion of a spring and modeling using differential equations. In later videos, I'll go over solutions to this and other examples. Anyway, that's all for today. If you learned, and like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy solution.